Okay. Hello, everyone. Welcome at this colloquium today with Dr. Daniel Schulte. In the introduction, let me explain a little bit the context. You might have heard that there is a lot of discussions, let me say, in the high energy physics community about what to do next with respect to the most powerful machine collider that we ever built, which is the LHC, the Large Hadron Collider, which is still running and is going to run for quite some time, in fact. And every physicist you happen to talk to, that person is going to have her opinion about what's going to be the next machine to go for. But very seldom it happens that that person is an expert about what kind of machine to actually pursue. We have the luck today of having one of the most prominent accelerator physicists that can really tell to have expertise on a very vast range of accelerator technologies and options for future colliders. He in fact started working on linear colliders back in the days for his PhD thesis on the linear collider back then called Tesla. Then he also worked on other projects. He moved to CERN, initially as a fellow, but right after as a staff. And of course, he's still today CERN staff. And he started working on CLIC, which is the linear collider project from CERN. But then he also started working on the Hadron Collider expected for, let's say, proposed for the next step of the LHC, FCC-HH. He also worked on other technologies like plasma acceleration, but other as well as other, if you want, collider ideas like the Large Hadron Electron Collider. But we have here him today because he's leading since 2019 the international effort on the design and the research and development on a very intriguing idea, which is the Muon collider. So without further ado, I leave the floor to Daniel for you.
Okay, thanks. So does the microphone work, first of all? Yes, okay. Okay, so thanks for the invitation. So I will try to tell you a few things about the Muon collider. So first of all, you might have heard that there were Muon collider studies before, actually in Europe already and in the US after, which then were not pursued a few years ago. And, but now there is a strong interest in Europe and also in the US. I will come back to that now. And so you may ask yourself, why now a renewed interest? And that is mainly for two reasons. One is the interest in going to really high energies for lepton colliders, many TeVs, and that actually becomes very difficult with any other approach. You know, the FCCE, for example, is limited to less than 400 GeV because of synchrotron radiation. And then the other reason is that actually in the past years, technology advanced and designs advanced in spite of the study not being like formalized, and that also gives us more confidence that things can actually be done. So the goal of the collaboration is to actually design a 10 TeV or higher energy collider, but we focus on one energy because otherwise you always get distracted and people avoid sort of putting together something in a level of detail that shows you that something doesn't work. So you have to keep one fixed point. And then maybe also some lower energy for staging purposes, and higher energies are not excluded, but at the moment we don't work on them, but in a moment when we have a solution for 10 TeV, we are going to switch. So very simplistic physics goals, and why is that interesting? You're certainly aware that electrons and positrons are point-like particles, like the muon. So they, in a collider, make the full energy available for producing new particles when they collide. And also, you have a very nicely defined initial condition, because you know these are the two particles that produce the event. There's a little bit of radiation that can happen on the way, but basically you have that well defined. If you look at a proton collider, in contrast, the protons can reach higher energies, but they are composite particles. And actually, they not just the 3 quarks, but then they have all sorts of C quarks or gluons inside. So they are like a bag of partons, and you collide these 2 bags, and then some of the partons collide, produce some event, and you get only a fraction of the energy available for your production of new particles. And also, you don't know a priori which part that is. So obviously, protons are more difficult in understanding the physics. And here on the right-hand side, you can see, let me see if I manage to deal with that. A comparison of what is an equivalent physics reach for a lepton collider. Sorry, could be muons or electrons, vis-a-vis a proton collider. So you see on the horizontal axis the energy of a lepton collider, and in the vertical the equivalent energy of a proton collider. And you see that a 14 TeV muon collider would be equivalent to 100 or 200 TeV hadron collider. That's rough, and now depending on the channel, it is somewhat different. The theorists have different preferences, but more or less 10 TeV muons is roughly similar to 100 TeV hadrons. The other challenge you should not forget is not just getting the energy, but you also need to get enough events in your collisions. So you need to increase the luminosity, which is a measure for how many collisions you get in your collider. And that luminosity has to go up with the square of the energy, because the likelihood of getting an event is decreasing with energy with the square of the energy. So you have to make up by having, with the square of the energy, more collisions to get the same number of events. So the theorist gave us some numbers here that we should attain for the integrated luminosities. And so for those of you that are not fully familiar with the high-energy colliders, what currently exists as sort of principal concepts are circular colliders, which is the usual part, with one exception. They were all circular, either with electrons. And as I said, everything is fine. You have the full energy available. But the limitation that you face with an electron circular machine is that forcing the electrons on the circular orbit actually leads to them radiating synchrotron radiation. And that radiation goes with the fourth power of the energy of the electron, and actually is only reduced as 1 over the radius. So you need to make the radius huge. And now, you may be aware there was LAP, 205 GeV center of mass collider in the LHC tunnel before. It was called the LAP tunnel. And there already, like 5% of the energy were lost per turn. So that means that you lose the advantage of circulating the beam if you have a loss that's comparable to your beam energy. And now if you go up in energy, that goes up with the fourth power. So you're limited, even with the FCC, with a 100-kilometer tunnel, at less than 400 GeV for electrons. With protons, you don't have that problem. They're much heavier, so they radiate much less. And you are limited by actually squeezing, sort of having the magnets to keep them going around. In the FCCHH, I should say, actually, synchrotron radiation was important. It was 5 megawatts and needed cooling power. But still, that is the first proton collider where that really matters. The other solution is to avoid a circular collider for leptons. So you accelerate the particles straight, you collide them straight, no synchrotron radiation to first order. Perfect. But you can see the problem right away. You collide the beams once, so you have to squeeze out many collisions in the one collision. And you have to get all of the energy, all the acceleration into the beam in one go, because you go through the straight only once. So that becomes very challenging as you go up in energy. So linear colliders are an option, but at higher and higher energies, that becomes less difficult, less easy. And now the muon is the solution. The muon is 200 times heavier than an electron, so you can go to 200 to the fourth power higher energy in the same tunnel. Perfect. Everything is easy, straightforward. You have the advantages of electrons, and your system looks like a proton collider. You're limited by the magnets. And we would have done that since a long time ago if it were not for the little fact that the muons have a lifetime of 2.2 microsecond at rest, which is not very long. And so you have to obviously do this very, very rapidly, and that's the challenge of the muon collider. Otherwise, we would have it. So how does the collider look like? The first thing is you need to produce muons. You don't find them in nature, so sort of in a easy form. So the way you do that is you use a proton beam. You produce a very high power proton beam. You send the proton beam into a target. In the target, you produce hadronic showers, in particular pions. The pions decay to muons. So you come out with a shower of muons. And now what you have to do is you have to capture these muons But they come from a shower, so it's like a football-size beam, and you have to make a very tiny beam that you can collide out of it. So you need a cooling section to get this big bag of muons to a very small beam. And then you have to accelerate it very rapidly to high energy. So you use linacs, recirculating linacs, and fast ramping rings to do that. Obviously, initially, you worry about doing the acceleration rapidly, because as your energy increases, the lifetime increases in proportion. And then you start worrying about costs, so you do it still fast, but somewhat less fast for cost reasons. And then once you have done that, you injected full energy into a collider ring, which you make as small as possible by using the strongest magnets that you can afford, so that you get as many collisions out of the muons as possible before they die. So that's the whole principle, trivia. Technology-wise, it's less trivia. Now, just to say, on the theorist side, there is a very strong interest in the concept, and the theorists enjoy that. And actually, I think they are still on their path to see that the physics case has areas that are very strong and that maybe they didn't think about before, so that you can find many papers there. Okay. Now let's look at the parameters. And I don't want to go into much detail here. This is more for reference. So these on the left-hand side were the luminosity goals, the integrated luminosities that we want to have. And then on the right-hand side, we see parameters that may be attainable. If we were sure, then we wouldn't need to do the study. I mean, then everything would be ready. We could say, give us the money, we build it. And if these parameters were indeed realized, then these integrated luminosities can be produced in a single detector in 5 years. If you had 2 detectors, 2.5 years. Now, there are 2 things. One is maybe that's a little overkill. You build a project for a long time, and then you run it only for a very short time to get that. And also, we may find on the way that some things don't perform exactly as we want. So there may be a little bit of reserve that we need and we operate longer. I should remind you that the FCCHH, for example, is planned to operate for 25 years, 5 times longer than that, or 10 times even with 2 detectors, okay? So, but just to give you this. So with all the challenges we have, there's also a little bit of lee room that we can use in the moment when we need it. But we have handed out only at the last moment in a way. So getting the energy, again, as I said, is one thing. Now getting the luminosity, getting the number of collisions is another thing. So I will show you one formula. Oh, no, actually, there's a second formula. Sorry for that. To explain how the luminosity is produced. So it's the number of particles that collide in a certain cross-section. And so this parameter depends on a number of different things. So let's start here. This is the number of bunches you inject into the collider ring per second times the charge in the bunch, number of particles, times gamma, times the energy. So this corresponds to the beam power. So you want a high beam power. And then this is the charge of the bunch divided by the longitudinal and the transverse phase space. Even if you didn't do accelerator physics here, you know that phase space is something that sort of plays an important role. And so what we want is we want as much charge and as small phase space as possible as the target. So that's the other part. Okay, so that's why we need to do the cooling to put particles together. And then comes here the magnetic field of the collider ring. If it's twice as big, the ring is twice as small, so twice as many collisions. The energy spread we can tolerate because that's maybe a detail already. If you can make that larger, that means you can make the bunch shorter, so you can squeeze it more at the IP. And then actually we happen to have here the energy again, gamma. So we naturally get more luminosity as we go up in energy. That's perfect. A linear collider, for example, will stay flat. Okay. So, but we need to get a dense phase space and a high current to get high luminosity and a high magnetic field. Okay. So now we think this is very promising, and I show on the left-hand side very rapidly. Collider is just there's footprint. So this is the FCC. This is CLIC at 3 TeV, 50 kilometer long. This is 90 kilometer long. This is the LHC. And here you see a 10 TeV muon collider. And actually, the collider is the small ring. The larger ring is the accelerator ring. It looks temptingly close to the LHC. So yes, we will look into whether we can put the accelerator ring into the LHC tunnel, but not at this stage, a little later. And it looks much more compact than the equivalent hadron collider size. So that gives us hope that it will be also cheaper. There are some more reasons, but this is maybe the most simple one. And then in terms of luminosity, let's compare to another lepton collider. This is CLIC. So here you have the luminosity normalized to the beam power. So you have the luminosity per power as the function of the collision energy. And you see in CLIC that's more or less constant. As you increase the energy of your collider, you need as much power per luminosity as before. And you want to increase the luminosity with the square, so you need actually with the square of the energy more power. Okay, for the Muon collider, we see that actually we gain more luminosity per power. So we win at the high energy side, while on the low energy side, actually, the Muon collider looks not so attractive. Now, in the US, they made a study to look at what they would expect to be the cost and the power consumption of these colliders. We are not ready yet to give them the numbers because we want to do the study to have a solid case. But they have experienced people in that committee, and they came up with some estimates which are consistent with what we might expect, but without promise. And you can see here different colliders. So there's the FCCE. You may have heard about that, which they would think actually would cost $12 to $18 billion in US accounting and use almost 300 megawatts of power. Here you can see the FCCHH, which would cost $30 to $50 billion and, well, use almost 600 megawatts of power. And here you have the 10 TeV Muon collider, which would use 300 megawatts of power, similar to FCCE, and cost 12 to 18 billion. So it would actually be as much as the FCC in terms of cost and power consumption, and give you the physics case of the FCCHH, if that turns out to be true after we did the study. And you can compare to a linear collider here, the first stage, which would be cheaper, 7 to 12, both for IOC and CLIC, less power, and you see that actually an initial stage of a Muon collider, say at 3 TeV, would have a similar cost. That's why we think about considering an initial stage and a lower power consumption. Okay, so that's the motivation. We can maybe go to these high energies with an affordable cost. Okay, now there has been actually a formal process to define what the R&D should be. So there were some committees, and the committee, the last one, looked into that and defined a roadmap with lots of work packages. You might not be so interested here. This is just to show there's estimates of people needed, of resources needed, all of that. And this evaluation said, we didn't see a showstopper. There are many challenges. It's not as mature as other approaches, but it could work. And so based on that, we started doing it. And this document says what should be done for that. So you can find it here. The timeline from that document, that will be revised, just to warn you. That's part of the study that we are doing currently. Looked the following. The first few years, the goal is to actually justify that it's worth to invest significantly into the concept. And then to have another European strategy in 26, as you can see here, which says, it's a good idea, and then to ramp up the resources and to do actually R&D with spending quite some money with a demonstrator, with doing prototypes of things. And then after that, you would be ready to go for a technical design and implement a project. Now, this may stretch a little bit, but the principle is the same. So our goal for the moment is to see, to make sure that it's clear whether or not the Muon collider is a great idea and should be pursued with putting more resources into it. This year was also made because it served the Muon collider as a plan B for CERN in case the FCC doesn't happen for whatever reason. And so the goal is to be ready for the next project with the Muon collider after high luminosity LHC in time. Okay. So now what is the collaboration working on that? Maybe to give you the idea of who is actually doing that. It's obviously many young people and some older people. But in terms of organization, there is a collaboration where a number of institutes, 70 or so, have joined. We got a grant from the European Union, which helped a lot with leveraging resources to do a design study for the Muon collider. It's not a huge amount of money, but it's very important that they supported us. People said there will be no support for any accelerator project or so. Okay, and we are certainly looking for new partners. And there will be actually a call to fund more of the R&D from Europe. And the new partners in particular, there is the US. But before going to that, these are the current partners. You see this is the long list. Many actually INFM institutes. Italy is well represented in there. In the US, the big laboratories cannot sign because they had this strategy process. They couldn't sign before, but some of the universities already joined. And now I think more are going to join the collaboration. So that's that. And So in the US, you may have heard by the end of last year, they said what their strategy should be for the future. So that's the recommendation by the expert panel. And basically, they said they should participate to the Muon Collider collaboration, and they should actually also be prepared to propose to host this project in the US, which is good, because then there would be a competition and collaboration. You work together on the technical part, and then you compete for who manages to get the funding agency, the country, to pay for the project. That made it to the New York Times. So there was something in Nature, and they also thought they can put it at Fermilab, so competing with Europe and working together. So that, I think, was a great step forward, and hopefully will ramp up the collaboration very soon. Now, what are the technical challenges that we have to face? Okay, there's the physics case. That goes, I mean, all the theorists, they sit by themselves and do that because they're excited about it. Then there is actually making sure that we don't have a problem with the environment. Come back to that. The background in the detector, to make sure that we can actually realize the physics, because if the muons decay, I mean, that has an impact on the detector. And then all of the systems that allow us to go to very high energy, because compared to the previous studies, they were focusing at much lower energies, where the Muon Collider actually is not so competitive. Now we want to go to really high energies, so we have to make sure that the project scales reasonably to there. And then comes all of the muon production and cooling scheme, which exists, which is more or less the same at all energies. So that has been studied to some extent in the US. Okay, first of all, what is the problem with the muons when they decay? When they decay, they produce two neutrinos and an electron or positron. Now, the electron or positron will be lost in the machine, and these neutrinos, they will fly through the Earth without any problem. So they come out at some point. Now, the problem that they have, typically neutrinos shouldn't do anything, but what you get is a very, very narrowly focused neutrino beam. So you don't want to point that to the same spot all the time, because it's like a tiny spot, but you don't want to like stand there or have somebody live there. So what you have to do is you deform the machine, so you actually avoid pointing to the same location for a long time. And by that, you can ensure that the neutrino flux itself is having a negligible impact on the environment, on people. Like for the LHC, there's a negligible impact on the environment around CERN. The one problem that you face is actually in direction of the experimental insertions, which are straight. You have many more neutrinos flying. So there you have to make sure that the spot you're pointing to maybe is owned, and maybe you can put a neutrino experiment there. Okay. So to address that, there's quite a number of experts to understand how much influence neutrino flux can have, to ensure that we can measure and control that, to see how the sort of directions of pointing of the beam look like, if you can use this dilution system, and how to find a location close to CERN that actually allows to mitigate the effect. So that looks actually quite good. The other thing that happens, you have now suddenly an electron or positron that carries on average 1/3 of the muon energy, but actually it's a wide spectrum, can be between basically 0 and 100%. And that is totally off energy. So in the arcs, it will be lost because it just will be bent more strongly to the inside than the muons. And if you're close to the detector, it will also be lost because you have these focusing lenses of the detector before the detector, and they actually overfocus these particles. And you have quite a large number, something like 200,000 per second, and bunch crossing and meter at 3 TeV. And when they get lost, they can produce electromagnetic showers, and you don't want them to reach your detector. So the way you deal with that is more or less you protect your detector by having tungsten masks that keep all of the showers, well, almost all of it, outside of the detector. You still get some residual impact on the detector. So the studies there show that the radiation levels are similar to what you have in Halloumi LHC, so something that is technically addressable. Certainly it would be worse with the FCCHH. And detector studies show that the impact on the physics, in some channels there is some impact, in some there is basically none. And now certainly the work is to make sure that also in the channels where there is some impact, that this impact is reduced to being negligible. Okay, but I'm not going to talk more about that. So now let's follow the beam and see what the challenges are in terms of real accelerator design. So the first is you need a 2 or so megawatt proton beam. Okay, that's not so unique. The power of the proton beam, that costs you some money, but in principle, that's not a big problem. But what you need is you want to have 5 pulses per second. So you need to take all of this power and condense it into 5 2 nanosecond long pulses. So the challenge there is to do that. And so we have experts working on a system where you basically inject that beam into a ring and you compress it in the ring, and then you extract a few bunches which you put at the same spot, and then you put it into the target, sorry. Okay. Now the target itself needs to take a, say, 2 megawatt proton beam. And so the first question is, does the target survive that? I mean, you send 2 megawatts of protons into a small, sort of a small dimension object. And so here you see that. So here you have the target. And the additional problem is in the target, you get all of these particles coming out at totally different energies and even negative and positively charged. So you put the target into a strong solenoid field because that means that all of the particles are spiraling forward and you can collect them. So the challenge is to have the target here and then to have a very strong solenoid, 20 Tesla around that. But a superconducting solenoid, if you imagine that you send 2 megawatts of protons into a target, lots of power is leaking out to the side. So you have to protect the magnet from that because a superconducting magnet doesn't like that. And so you need to put shielding between the magnet and the target. And that means you need a large aperture of the magnet, which makes the life here more difficult. So that's the principle of the target. And now let's look into a little more detail how the target looks like. It's more or less a graphite rod here. You can see that. It's supported at some locations. And the beam is really sent in from the one side. So here it's like that. So it's like a pencil beam going into the target. And actually, calculations show you use graphite for that it can sustain the energy that gets per pulse. Because graphite is extremely robust. And so there is no problem with that. So these studies have been done. You see here, these are simulations of the target, and they show that it can sustain these pulses. And then you need to identify how thick the shielding needs to be. So that has been done. And you also need to ensure that the shielding itself is not heated up too much. So that's done. The vessel around the shielding, it's fine. And then the window for the beam to come into that. And so here, this window is the only place where we need some more work in order to ensure that it's not heated up too much per pulse. So that's ongoing. But the target looks pretty good. It's extremely challenging, but we feel that it could be done, and we are probably going to look into an alternative now, actually, hopefully together with INEA, which is using liquid metal jet instead of graphite, which can take even more, so lead or something. In the past, mercury was used, but mercury has the problem that if something goes wrong, then you have liquid mercury all around because it's liquid at room temperature. Well, if it's liquid lead and something goes wrong, then it drops and becomes solid lead. And so you have much less of a problem. Also, it doesn't evaporate like mercury. I mean, if you have mercury on the ground, you have to get rid of it because otherwise you inhale it. Okay, so that is fine. Then the next problem is the cooling. So how do you do how do you get the muon beam cold? And the idea is very simple. It is used normally in damping rings, but in damping ring, you circulate the beam with radiation a long time around, but we don't have time. So what you do is you send your beam through a target. It's a thin target. With muons, it works because the muon basically loses some energy, but it doesn't react otherwise much with the target. And so what happens is you have a muon here with this momentum. It has a transverse and a longitudinal part. You go through the target, and you radiate in the direction of, or you lose energy, momentum in the direction of the motion of the muon. So you lose this blue part. Maybe I should make that red to look more impressive, I don't know. And so your transverse momentum and your longitudinal momentum both shrink. You have this now. And then after your target or absorber, you go into an accelerating cell, and there you restore the longitudinal momentum. You only accelerate forward. So what happens is that the transverse momentum has shrunk. And by that, you change transverse momentum. By that, you cool the beam. And then changing transverse momentum also means that you can reduce the transverse size at some point. No, it's the canonical conjugate variable. So by that, you get your beam cold. many stages of this. So you see here, actually, the system is relatively complex. The beam actually comes here from the left to the right. No, this is still the, so sorry, no, this is still coming from the right. It does that on the next one, sorry. Now, there's one problem. The cooling process, so this is the second formula, and it's only for people that know Beta Heitler, the Bloch. So here you have actually the cooling term, which is the fact that you lose energy and therefore transverse momentum as you decelerate it. But then you are aware that there's multiple scattering, mainly on the nuclei of your matter. And that gives you some additional transverse heating that you don't want. And that limits how much you can cool. And now one of the nice features is if you put this into a very strong magnetic field, then inherently the angles of your particles become relatively large. And that means these additional scatters don't matter so much. So that's why you put everything here into a strong solenoid. And the stronger the solenoid, actually, the smaller the heating term and the longer you can cool. But at some point, the heating from multiple scattering limits how much you can cool the beam. Otherwise, we would go to really small dimensions. So this principle actually has been tested in the UK in a test setup where you had muons, actually individual muons coming from the left. They go through the solenoid, and in the middle there's a place where you can put an absorber, and you diagnose the particle before and after. And so this here is showing what happens if there is no absorber. You have actually this distribution of offsets before, and then the green one after. So these particles here are not existing anymore because they are lost on the walls. So that's why. But you see that these curves agree up to some relatively large action. Oops, sorry. And then now you put an absorber. So the initial distribution is the same. What you can see is now the distribution after the absorber has actually changed. There are more particles at lower amplitudes than before. And well, there are fewer at high, but this is strange. No? That is the cooling effect. So a particle that had a high action, large angle when it came in, actually comes out with a smaller one, and therefore it has been cooled. And so that's a proof that the principle works nicely. And actually, calculations show great agreement with the experiment. So this was the setup of that, and this is the result. So it was published in Nature. Okay. Now, the actual system is a little more complex. It's not just this one stage. So it has a number of stages. So you start from the target, you collect the bunches, you cool. And then actually, by cooling, you produce a few bunches in a row because the things lengthen. You put them together, and when you put them together, you have to put them side by side in phase space, not in one single spot. And that's why, after this cooling, you put a few bunches together. That's why your phase space increases, both. Sorry, I forgot. This is the horizontal phase space here. So transverse, and this is the longitudinal. So what you do is you reduce both the transverse and the longitudinal phase space, and then you put the bunches together, so it becomes larger, and then you cool it further. And then at the very end, actually, what you do is you say, okay, the longitudinal phase space is very small. I cannot profit from that, but the transverse still needs to be cooled. So you go and let just the transverse shrink at the cost of the longitudinal increasing. And each of these systems consists of many of these cells. Actually, several stages of sequences of these cells. Okay, so that's the way it works. So here you see the beam now coming from the right, from the target, being cooled in stages, coming out like that. Okay, so this only works because, well, you might know Liouville's theorem, no? That the fact that the phase space density cannot be changed. But the way it is changed here is you have interaction with matter, and that allows you to change it here. You couldn't do that otherwise. And here at this location, you do it without matter, so that's why putting bunches together increases the phase space. Okay, now what is the technical problem with that? First of all, you have to make these cooling cells as compact as possible, because any path length costs you particles. More muons die if they have to fly longer. And so here you see how compact such a cell could look like. You have an absorber, you have the RF cavity, and you have the solenoids around the absorber all close together. And you already can see at this location here that that's a PowerPoint design. That will not work in practice because you need some space. You need to put cryostats because these magnets are superconducting. Okay, so that needs work. And then, in addition, RF cavities don't like to operate in a magnetic field. Typically, they want to avoid that because that means that if you have a breakdown in the structure, then all of the electrons, they go along a field line and hit the same spot on the other side and go back and forth. And so dealing with that is a big challenge, but that actually has been done in the US. They looked into 2 different designs, one using beryllium, one filling the cavity with high pressure hydrogen, and both actually avoid this effect. So you can operate the cavities in these very strong solenoids with the absorbers there. Another problem you have to worry about is heating the absorber, because if your muon beam becomes very small and it deposits momentum energy, then certainly it heats up the absorber, and you have to limit that. So that is another thing that you have to study, how you heat up your hydrogen. At the end, we cannot use liquid hydrogen anymore, but only gas, which we have to tailor the density to what is acceptable, and you worry about the windows, but those are being tested. So, okay, these are the technologies that have to be put together. The other part is you need to put together the solenoids. And so it's very unique, because normally solenoids in an accelerator are not so, I mean, you need them in specific places, but not so often. But here they appear in all sorts of places. So maybe let's start here on the right-hand side. There is this huge solenoid around your target with a 1.5 meter or so aperture size and 20 Tesla. And so there is a design to use high-temperature superconductor for that instead of conventional low-temperature superconductor that one is using right now, because high-temperature superconductors are developing now, and they actually would allow I mean, they make cooling much easier and more efficient. And this looks actually very close to, or resembles closely to what is needed for fusion. This here is a coil for ITER, a model of a 13 Tesla low-temperature superconductor coil that they want to use there. So that's great. And such a magnet here in HTS would certainly be excellent for that. So there is quite some synergy between the two, and we hope that this can be used for the magnet development, because both fields will profit from that. The other part where you need solenoids is at the very end of the cooling. The field in these solenoids needs to become higher and higher, because you want to suppress this heating effect from the multiple scattering more and more. So you need to go to 40 plus Tesla. Currently, any good magnet laboratory makes something like 30 plus Tesla, and they aim for 40 plus Tesla for the next round. So that should work, but it still is work ongoing. So here you see an example of a 32 Tesla from the US. And the theoretical limit, the magnet people tell us, is 55. But for the moment, we use 40 in our design. But we are certainly going to push further from that. So this is just to show you that there's quite some magnet work going on in that. Okay, after the cooling, now you go into the extraction. And so the extracting complex consists of a sequence of linacs, recircular linacs. We don't really have huge resources working on that. And then come actually a sequence of rings to extract. And those rings will be ramped up with the beam energy. So you inject the beam at low energy, all of the magnets have low field, and then as you increase the beam energy, the magnets have to ramp up in field in proportion to the energy of your beam. Now the issue with that is this ramping up has to happen in milliseconds. And actually in the initial ring, which is small, it has to happen faster than in the last ring, which is bigger. And because it has to be so fast, you can normally not use superconductors, because like the LHC, I mean, you need 20 minutes or so to ramp up the machine. So that's orders of magnitude off. So what you have to do is you have to use normal magnets, because normal magnets can be ramped that quickly. And then they need help from iron. So that means that your magnetic field is limited to 2 Tesla, roughly. And that's why the accelerator ring is bigger than the collider ring, because it's limited by the strength. I mean, the integrated field all around the ring is the same as for the collider ring, but it needs to be bigger because they need to ramp more rapidly. The collider rings ring magnets are static. So that makes that. Now there's one trick that you play. Actually, you put in a few superconducting magnets between your normal ones. So they bend the beam inwards. And then what you do is when you start, you use the normal magnets to push the beam outside. So you see that here. And by that, basically the two cancel more or less. And because they cancel, it means you're adapted for the small initial energy. And then what you do as the beam energy increases, you ramp the normal magnets down, so they do less harm, and then you ramp them up to help the superconducting ones. And okay, that looks a little complicated, but the advantage is you win a factor 2 in effective swing of the field, because the superconducting ones are very short. And so you go from minus 1.5 Tesla to 1.8 or so to plus 1.8, and by that your change in field is a factor 2 larger, so you need half as many magnets. Perfect. Okay, you can do that on a piece of paper afterwards if you want. So sorry for that. Now this looks fine and the speed can be obtained, but there is one other huge problem. If you look at the total energy that you have in the magnetic field in all of these magnets, and you compare this total energy to the total energy in the bunch of the muon beam, it is way more in the magnets. And that's always the case in any collider. So you talk about something like 100 megajoule or so, and you pump that into your magnets 5 times a second. So that would be 500 megawatts. And so obviously, what you have to do is you have to take this energy from the magnets, put it back into some storage device, which is called power converter, and then use it for the next pulse again. Because if you don't do that, your machine will be using way too much power. So these power converters are an extreme challenge. Recovering the energy with high efficiency and putting it back into the magnets, and also having little losses in the magnets is critical. So that's one of the fun challenges. And actually, there's a whole team of people working on that, on the design of the optics, on the dynamics with the RF, on the cavity design, the power converters, the magnets. You see here, the magnets actually are designed in Bologna. Okay. So first of all, with the acceleration, you have to see if that can be done. And one of the challenges there that I should have mentioned before, as I said, we want to have a very high phase space density. So that means we also want to have a very high charge in the bunch, because then it's easier to get the same size to get high phase space density. So now you worry about the acceleration, because actually in our case, what happens if you go through a cavity with the bunch once, you take out a few % of the stored energy in this cavity. So that means that the field of the cavity, the accelerating gradient, changes by half that much. I mean, because the energy goes with the square of the gradient. So you have to worry about extracting a few % of the energy of the storage device each passage, and you have to find a way how to deal with that. And the way they do that is by making an optic such that when the bunches come through the cavities, they change the longitudinal position in the bunch a bit each time, and by that they average out. So they see the peak field when they're up front, and they see a reduced field when they're at the back, and if you average enough by letting them move forward, backward, then that's fine. So the people tell us that this can be done, and that actually the cavities from the IRC with 1.3 gigahertz might be useful for that. I never believed we could use such a high frequency. Higher the frequency, the less energy stored for the same gradient. Okay, and the other thing that also needs to be checked is the beam actually stable? Because if you go through a beam pipe, there's a limited conductivity on the end, and so if your beam has a little offset, then actually it will get an additional kick from the beam pipe that makes the offset worse and worse and worse. And so this also has been studied, and it shows at which radius and which surface material you're safe. And so it shows that actually with copper coating and a reasonable aperture, we are fine. So this here is showing the minimum diameter that we need, and you see it's like 2 centimeters. So, and this here is the damping bit, because if your instability grows very slowly, then you use some feedback to cure it. So I mean, it will always grow. But if it's slow enough, then you deal with that. Okay, so that has been looked at. So we believe the bunch can do it. Now let's look into the fast ramping magnet system. And that's actually totally interesting, because the magnets and the RF, they have to work together, because the RF increases the energy of the beam, and the magnets have to follow. Now, the magnets would like to have a sine-like swing, just oscillate like a sine. And the RF would like that the energy increases linear with time. If we do that with the power converters, so here you see the power converters, and we force them to be exactly linear, then the cost of the electronics you need to ensure that is huge, so and so many billion euros. So that we found is a little too much. So what you have to do is now you have to really synchronize and to make an integrated cost model where the RF people say what they can do and how much that will cost, and the power converter and magnet people do the same, and then you find what is the optimal ramp-up curve to work together. So they actually came up for the power converters with some novel designs that would be more efficient and cheaper. Okay, this is for the people that like power converters in detail. Here you see the magnets. They're relatively straightforward, but again, you want to make them very efficient and with low loss. And just as a side remark, I said superconductors cannot be used, but actually for the biggest ring, something like 300 to 400 Tesla per second would be good enough. And what they see at Fermilab is that with HTS, the new superconductor technology, you could come into that regime, and they can probably push it further. So they had some measurement which was actually very close to what we would need, and they can probably be pushed further. So that's an interesting development to make the losses in the biggest ring even less. Now let's go into the collider ring. And the problem in the collider ring is that you focus the beam to a very small spot size when you collide. So this here is the optics for that. For those people that like accelerator optics. You have a relatively large energy spread of 1 per mil. For a collider ring, that's relatively large. So you have to worry about the chromaticity of the system. And then you also have to make sure that the bunches remain very short, because if you focus them a lot, then the waist, the focal point length is very short. So this here is the optics that you have. And maybe just for you to know, typically such a diagram which shows how the beam looks like at collision would have all sorts of nice ellipses here. And because of these squeeze requirements, we see that actually we start to develop something that's a little different from this optics. But it still looks very nice. So that seems like possible. We assume for the moment that for the 10 TeV collider, we would use very high field magnets to make the collider ring small. However, you could use some lower field magnets that are closer to what already has been used for the high luminosity LHC, for example. And you would lose some performance, but the magnets would be way simpler. So there will be, in the end, some trade-off between how much do you squeeze out the last little drop and how much do you pay for that and when do you stop. So, and it was actually a 3 TeV design that we believe works from the US people, and we are working on this 10 TeV design. It seems to be okay. Now, also, the collider ring itself has some technology. The biggest problem, as I said, is the fact that the muons decay, and you have these electrons and positrons, and they get lost, and they will hit the superconducting magnet and heat it up and radiate it. So that has to be prevented. So you have to put some shielding inside to stop the beam, which is here, from hitting, or these lost particles hitting the magnet. And so you put some tungsten shielding in here, and that drives the aperture of the magnet. The magnet has to provide additional space for that. And so there has been a design for that, and we studied how much has to be lost. It's like 500 watts you lose per meter, and you have to reduce it by roughly 2 orders of magnitude. So that has been studied. And then this determines how big the magnet has to be. So it's something like 16 centimeter diameter in the gap. And that's more than in many superconducting magnets. So what you have to do now is, typically these coils are in a way self-supporting. So if you make the magnet bigger, you get more stress and more force on the coil, and then it starts at some point to stop being superconducting. It can even break because of the stress. So what you have to do is you have to use stress management, which is a good idea for anybody. But for the magnets, it means that you support the coils not just by themselves, but you help them by putting in more material. So what you do is some design like that. This would be a typical design where you have the coils and they support themselves because the magnetic forces, they push on them. So you break them into small pieces and you put your support structure in between. That makes sure that they don't suffer too much stress. So this is ongoing, and we hope that this will work out soon. Okay, so let's come to the CDR phase, the next phase, the R&D and the demonstrator. So this is the phase we would have with the next European strategy. So the most important thing to show is actually that this cooling scheme works also in terms of engineering. It's not just theoretically, but there were many, many little problems that actually catch you if you don't think about them. And so that would be a facility that could be, for example, located at CERN. So there are 2 locations, one on the site, which is not perfect, but would work, and one better one that is off-site, but on the country. This land here belongs to CERN. But here we would need to spend more money on civil engineering, and this would be just cleaning. So that's being studied. You see there is some drawing of how that could look like. The beam comes from here. These are the access shafts. You would have the RF equipment here and the beam there. Okay. It could also be at Fermilab. So the people there looked into how it could be there. And it looks, the facility, we have some dimensions that look like that. More or less, you produce muons in the target. Then you do some manipulations. You measure also the muons so that you understand the beam. You go through some 50 or so meter of cooling. And then you diagnose again, because you want to see what happens to the muon in this cooling. And so that comes here. This is a bit harder. Okay, and so this here would be all the cooling. Okay, so that could be such a facility. The other thing is we try to see how the implementation could be done. So this timeline that I showed you initially from the roadmap will change. And things that are most critical for determining the timeline, except for the budget, well, that's not technical. Things that are slowed down if you don't get the budget, are the magnets, their development. It's this cooling scheme and its demonstration in integrated facilities, and then the detector and its technologies, just because the better that is, the more, the better the physics performance will be and the more robust the whole design. So for the magnet, we more or less had the experts agree that they think the technology would be ready in 15 years from now, except for the collidering, the highest field magnets. So if for the collidering we use some older technology with somewhat less performance, then it also would work. So that is okay for the 3 TeV or for a reduced 10 TeV stage. But all the other magnets, they believe, could be ready in 15 years if things go well. And for the collidering magnets, they didn't agree. So some people said it could be faster with the new technology, but some people said maybe not. Such a staging would look like that. So here, first we have the energy staging, where you actually have a 3 TeV collider. So you start with your injection. You have 2 stages or so of acceleration, and then you have your collidering, which I exaggerated a little bit in its racetrack shape. So the experiments sit in the straights. And then if you upgrade that in energy, what you do is you build an additional accelerator ring and a new collider ring. So the old collider ring is not used anymore, but all the rest of the complex is reused. And that's also, if you look at these dimensions, this is why we believe this is half the cost roughly of that one. It would sort of split the cost more or less in 2. Or the other one is you build a 10 TeV collider right away with reduced performance, which you then upgrade later with more, with better magnets. Like for high luminosity LHC, you increase the luminosity with improving the interaction region. The site studies, I was referring to the neutrinos, sorry. So indeed, at CERN, we found a site that would mitigate the problem with the neutrinos going in the direction of the experiments. That now needs to be looked at for geological limitations to make sure that it works. And at Fermilab, the main concern was that the collider would fit on the Fermilab site, including the acceleration, and that seems to be the case. So they will do some more studies. Okay, so in conclusion, the Muon collider is a unique opportunity to go to high-energy lepton collisions. In particular, the highest solid E plus and minus proposes at 3 TeV and would cost more than 10 TeV Muon collider, if the cost prediction is correct. And we are working now towards that on the design, the technology, and also defining what needs to be done in the next phases. And there is this collaboration, and then we will obviously enlarge it with US partners, but we hope also in Europe and Asia to find more partners. So you're welcome. And actually, like always, there are web pages and our secretariat that will help you with that. Okay, that was what I had to say.
Time for questions.
A quick question. Over the next, let's say, 5 years or 10 years, what are the competencies which are most important that would contribute more to the project in this phase?
Okay. I think magnets are a key technology that really needs to be strengthened. It is, for the accelerator design, we have gaps, especially also for the muon cooling. It's a very complex system, and we more or less said, we take up what the US did and we polish it a little bit, but we cannot do much with the existing resources, and that, I think, needs to change. So it's the accelerator physics. Then, obviously, for the detector, I think it's good to try also new ways maybe to reduce the background impact. Again, in some cases, I mean, it's not disastrous, but it's certainly something that could be improved using maybe novel approaches. I think that these are the main areas. But to be frank, we are stretched in every single part. I mean, we are a much smaller study. Our budget at CERN is smaller than the one for Wiik, which is just the plasma. We are a really small study. We get then this EU support, and we get more partners. But it's yeah, basically any expertise can contribute in a useful way. I mean, that's what I say. There are some that are more in our mind, but like the cooling, there are little things that should be studied. If you use this mover system, the cooling has to follow the movement of the beamline components. So there is a study all by itself for some cryogenics experts, as an example. Yeah.
So I intercept the question. So in your opinion, what is the aspect that is most on the critical path currently? The one, if you want, that would make somebody against the project to bet on the failure of the project itself.
I don't know.
Wait.
This is hard to say because yeah, no, it's a bit like we still face a number of challenges for luminosity, where each individual challenge is not going to stop the project. But if all of them don't work, then you're in trouble. That's like always, you know. So yeah. For example, what I would like, I mean, and since we discussed a bit with the ENEA experts, our target currently is this, the baseline is this graphite target, but it would be great if you could double or triple the charge that we send into the target each pulse, because it gives us twice as many or 3 times as many muons that we can lose on the way, basically. And I should say that the fact that we have to reduce these losses implies quite some constraint on the design and the cost. Like the acceleration in these rings has to be really rapid because of that. If there was a little bit of leeway, that could maybe make things much simpler, cheaper.
Thanks very much for this really interesting overview. So why free TV? Why 10 TV?
Ah, okay. This is a very good question. So 10 TV, okay, more or less, we could also have picked 14 TV based on the plot that I showed. 10 TV was a little bit big because it's somewhat cheaper and easier, and I believe the cost of the next project is a big challenge. So you want to do it in small steps. And also it was fair to give the hadrons a chance in a way, because 14 would be better in all ways, I would believe. So it was a little bit that, but it's a round number. Like if we would find that 8 TV would nicely use the LHC tunnel and everything would be way cheaper, and maybe we go to there. The US study, the P5 actually said 10 TV parton center of mass collider. So for them, 10 TV muons or 100 TV protons is the same. Okay, so that's that. The 3 TV was a little bit, because cost-wise, it's roughly the half point, because you have also the injectors, so it's not just linear with energy. And also because there was the CLIC study before, it still is, which was 3 TV, and so it felt like, why not compare there? And going much below, then the muon collider doesn't look so interesting. I mean, a 500 GeV muon collider, yeah, you would do that if you go to the high energy anyway, because you would get less luminosity, because at low energy you're punished by this scaling with energy. And much higher, then it's not different from the 10. So it's a little bit, obviously if the LHC finds something, I mean high lumi or so we will change the plans immediately according to match that.
But can I make another question? And not that you already mentioned that it's maybe not so interesting to go to low energies. I remember that a long time ago there was Carlo Rubbia who told us all about Muon collider at the Higgs mass. What about these ideas?
Yeah, so this idea, okay, that works differently than scaling normally down, because your luminosity is still very much reduced, but you can produce the Higgs on resonance by just mu plus mu minus, without having a Z in between. So that's why the low luminosity would have been fine. Now, the problem there is it is not that much less challenging than the high energy. The challenge is somewhat different, so it needs additional resources. And it's also a regime where linear colliders or FCCE can do a good job. So it would have been, I mean, it's attractive in the moment when you say we go for the Muon collider anyway. Then you add that and fine. But it's like you choose the wrong weight class for your fight. You go where you have a unique selling point. And if the others fail to have the low energy Higgs factory, then you come back to it.
A question for a student.
Good afternoon. Thank you for the presentation. And I wanted to ask, we have seen that neutrinos are a problem to overcome. We have to shield them, etc. But could a Muon collider also be used to study neutrinos? Maybe put a detector in some place in the Muon collider to study them?
Yep. No, when we try to reduce the flux, we were told that please don't do that, we want to put a detector. No, so obviously you can consider putting a detector in that location. We try to find the synergies. The problem is we cannot do much on that because we don't have the resources. Also, even on the way, if you have such a test facility, a demonstrator facility, you produce still plenty of muons, which you could use in a facility, something like Newstorm. So one of the ideas was maybe you have your test facility where you send the muons in, and every other pulse or some time of the operation you dedicate to sending the muons into a decay ring where you then have a Newstorm type experiment. So absolutely, we would be happy to have support on that, but the only requisite is we are so small as a study that we need somebody else to have the resources to do that properly.
Thank you.
Other questions?
Okay, so you presented just a comment, you presented the demonstrator, which is a small, probably not so small facility. Can you comment if it is possible to start, let's say, this demonstrator, for instance, starting as a big facility, as is shown, step by step?
Absolutely. Yeah, for the facility, I mean, the first thing you really need to do is you need to test an engineer, I mean, a real design, a real prototype of such a cooling cell. Because putting these high field magnets together, which are superconducting, so they are in a cryostat, together with the normal conducting cavities and the absorbers, and suddenly you start worrying about, where do I put a vacuum flange? That's totally annoying, or even a detector design, you're suddenly real. And and then you want to power that, even without beam. You just want to see that the cavity behaves the way you want and it maintains the gradient in this field. And so for that, indeed, we would need a bit of funding to have a site, to have the power source. I mean, we talk about a few millions there, so it's relatively cheap. But we don't have the budget at this moment. So you could start with that, and that would speed up the whole demonstrator complex by a lot, because you have to wait for this result before you then actually can launch the production of a few of these cells, which you put into the demonstrator. Yeah, for the moment we try to manage to keep sort of to get a reasonable budget at CERN. And we have a few proposals. I mean, like in Milano, there is interest to actually have a scaled version at a different frequency, so somewhat cheaper, of such a RF test station where you have the solenoids and you have the cavity. And what is new compared to the US study, they had a test, but then they disassembled it, so it doesn't exist anymore, is to have two coils so that you can not only test having a homogeneous field, but you can also test what happens if the field flips, if the direction of the field changes, which is something you want to do actually in a number of locations in this cooling for some beam dynamics purposes that maybe we don't discuss here. So absolutely. The other thing is we certainly need to get going on some of these HDS, the cable development on the using the cables we bought. But you see our budgets then are typically spending 20 kilo Swiss francs on buying some cable at this stage. We hope that with some EU project now that might improve in the future.
If I can share the comments that we were making before at lunch. So this is a project where the pressure is from the bottom up. So it's more like the community likes a lot the project. And that's why even though the budget is limited, there is still a lot of studies going on, a lot of interest. There are some other projects where the pressure is from the top down. And there you have the money, but you have a bit less probably passion in the participant probably. Other questions? Okay, if not, let's thank Daniel again. And thanks everybody for coming. Bye-bye.